Hello, everyone. Welcome to our second talk in the event Understand Deep Learning. Our intention here in this event is to uncover the secrets of deep learning, to explain how and why deep learning works the way they do. For that, we have today Jeremy Bernstein. Thank you, Jeremy, for joining us today. Thanks University of São Paulo and the Institute of Mathematical and Computer Sciences for the help in promoting this event. Jeremy Bernstein holds a bachelor degree in experimental and theoretical physics from Trinity College and a Ph.D. in computer and neural systems from Caltech, and is currently a postdoctoral research at the MIT. His research focuses on mathematical foundation of natural and artificial intelligence. His main interests include discovering the computational and statistical laws that govern intelligence, both natural and artificial, with the aim of designing more efficient, automatic, and practically useful learning systems. Welcome, Jeremy.
Thank you. Yeah, thank you for having me. Could I double check that because I'm more than happy to, have people ask questions or interrupt me during the presentation, but is there a way to do that?
The way you prefer, we can do the Q&A section after the presentation or during, whatever.
I personally prefer during, because then
okay.
yeah.
That's fine. I will keep you noticed when some questions appear. Okay.
Okay. Shall I begin?
Yes. Please.
Okay. Let's see. Okay, do you see my screen okay?
Okay, now we see.
So, yeah, I'm Jeremy. I'm a postdoc at MIT, and I think a lot about neural networks and on quite a theoretical level, but with the intention of designing better algorithms, in particular, better training algorithms. So, like, some of the talk is interactive, but here I have a question. So why do these airplanes not this is a flight map of the United States, and there's pictures of the airplane trajectory going between different cities, and I wanted to ask, why are the trajectories of the planes, not straight lines. They seem to be curves. Yeah, I think maybe I'm not sure if there's a way for people, like, if anyone has, like, are people able to just vocally ask or questions or interrupt? If they're not, it's fine. But just my preference is for people to just be able to.
Yeah, unfortunately, but we don't have this option here. But I will keep you notice, and I'll say
Okay.
the questions out loud here.
Okay. Well, let me just ask then, and then I mean, let's see if it work. If the system works. Like, can anyone tell me why?
Um, excuse me, I kind of didn't understand your last point.
So there's a question on. Sorry, there's a question on the slide.
Okay.
Yeah. Why are these trajectories of these airplanes in the United States not going in the
Yes.
straightest line between the
Yeah,
two?
we have here the rotation of planets, the Earth's curvature.
Yeah. So the answer that I was looking for is the curvature. The curvature of the Earth. So the idea is that we're looking at a map of the planet, but the actual Earth is it's not a 2D map. It's a it's a 3D. It's a manifold, or it's a surface. And when we project the map when we project the surface of the Earth into a two-dimensional representation, there's some kind of distortion that happens. And in math, there's a tool that sort of links these two worlds, the projection or the atlas to the to the surface, the curved surface, and they call it a metric. Essentially, it tells you how distances on the map relate to distances on the curved surface. And what I want to argue is that this is really a tool that we're missing in deep learning, like actually having a good metric. So I want to make an analogy that somehow there's a similarity where on the left we have the neural network, with it's got an architecture, it has some weights, and then by analogy, the kind of real thing that we really care about is the function implemented by the neural network. So what if we could build a tool that could map between these two descriptions of things, like our description of the neural network and what we actually want from it. And this is just very high level. I've not really even explained what we mean by a metric. So what is a metric? Actually, for the purpose of this talk, I just mean a norm. So in particular, given a neural network with outputs y, inputs x, and weights w, we'd really like to be able to control the output of the neural network. But unfortunately, we only control the weights w. But the idea is, what if we had a norm, a distance measure on the output of the network? Could we build a norm or a distance measure on the weights of the neural network, so that the change in weights in the weight norm is predictive of the change in outputs in the output norm? And if we could do this, it would be very useful. And the thing that I'm trying to propose at the moment is this idea of what we call metrized deep learning. And what I mean by this is a kind of building a machinery that places norms on all the spaces inside a neural network in a kind of good and meaningful way. So what do we mean by what does that even mean? So if we have a neural network here think about passing the inputs in from one end and the outputs coming out the other end. Some of the natural spaces to think about are the activation spaces, which we think of as the hidden vectors, or the input vector or the output vector. My claim is we sort of know how to equip these spaces with distance functions, here I say we know how to metrize them because they're quite simple spaces. They're just like kind of simple spaces of vectors. If you do deep learning, you hear about techniques like layer norm and RMS norm, which is basically saying that it's basically saying that we know how to normalize these things. Similarly, we have these tensor spaces, and these are like the weight matrices which map between two consecutive layers. And what I claim is people in applied math know how to metrize these spaces, and we talk about induced operator norms. Theo, is it like, are you still there? Like, I'm so used to giving talks where there's some kind of interaction that I'm finding it difficult to do it without at least talking to one person and we go through it.
Okay.
I just feel like it will help to just know if I'm going too fast or if people are following or.
No, it's perfect.
Okay.
I'll let you know if someone say something in the chat here.
Thank you.
Okay.
And like if people in the chat, because I can't even see the wait, maybe there is a way for me to. Oh, okay. Now I see the chat.
Oh,
Wait, I
very
was
good.
on the wrong.
Very good.
Okay, can people tell me if I'm going too fast or going too slow? And that way, because otherwise I have no way to gauge if people are following the talk or not.
Okay. It's going all right. Yeah.
Thank you, Pablo. That's what I. Thank you, Juliana and Shamila and Louise. Okay, let me and Don. Thank you. Okay, let me keep going. So what I claim, the thing, if we know how to equip distance measures onto the activation space and onto the individual weight spaces of each layer, the thing that I claim that we don't know how to measure distance on is the full weight space of the full neural network, where we combine all of the layers. And just as some high level claims that I think if we can do this, if we can solve this problem, it would be really useful to help us do low precision training. Thank you, Samuel. Because there we need to know how finally to discretize the spaces inside the neural network. And I claim that if you want to discretize a space, you need to know on what length scale things change, and having a norm would be useful for that. This is just some motivation. And similarly, another thing that people are interested in is having robust models, because at the moment we have this problem where you can do very minor perturbations to the inputs to your model, and then the classifications completely change, or the model outputs completely change. And again, I think for this, the fundamental question is about understanding if I perturb the input to the model, what length scale of perturbations am I allowed to do, and should I expect the model to be robust on? And I just think this is another high-level problem that could benefit from having a good way to measure distances inside the model. But the focus, actually, those were just some motivations. But actually, the main thing I'm going to talk about is scaling. So this is what people are really interested in at the moment, is to train very large neural networks, and it seems to give us all of these amazing behaviors. And this is just the slight motivation slide where we even see in the natural world that bigger neural networks seem to be more intelligent, and actually the African elephant is actually, if you're interested, the organism with the most neurons on the planet, if I remember correctly from Wikipedia. So it has, anyway, this is just this idea of bigger is better. And like what these technology companies are doing is they're just trying to get the biggest supercomputer they can, scrape as much data as they can, and train the biggest transformer model that they can. And it seems to be giving us these very powerful AI models. But what I want to point out is that there's some issues that you run into if you try to scale up your neural network. So one of the ways to scale a neural network is to increase its width. And if you do this, you often see that that basically this is a plot where I'm plotting the training loss against the step size used to train the model, the learning rate used to train the model, and the different curves and neural networks of different widths. And what you see is that if you increase the width, so going from the yeah, you can see my mouse. So this dark blue curve is the smallest width, and this yellow curve is the largest width. You see that the best performance you get actually improves by increasing the width. And essentially that's good. That's what we want. What does beau tarde mean? Does that mean too slow?
No, it's good evening.
Oh, okay, beau tarde.
Yeah.
Okay, basically increasing the width improves the performance, but what you see is that the step size that you need to use to get the best performance is actually drifting. And it's so if we train a network at width 32, you use this step size to get the best performance. If you train the network at width 1024, you need to use this step size. So this is annoying because as you make the model bigger, you have to change the step size, and you often have to tune to. This is a big nuisance, and it makes training really large models kind of annoying. And another way to scale the model is to increase the depth or the number of layers, or in a residual network, the number of residual blocks. And naively, if you do this, you can see a different problem where the training actually gets worse as I scale the network rather than better. And so this is another nuisance. So we wanted to really understand the sources of these problems and to try to fix them. And that's another motivation for the work I'm going to tell you about. But before that, I want to give you even more motivation for the way that we think about the problem. So here I have, some resistors. If you're familiar with electronics, you might recognize this as just some resistors in series. And we have a rule for how to combine resistors in series, which is to add the resistances. And similarly, if we put resistors in parallel, we have another rule which says if you add resistors in parallel, then to get the total resistance, you add the reciprocals of the resistances. And then, okay. And this, with these circuit rules in electronics, we're able to build very complicated electronic circuits and reason about the properties of the complicated circuits. But in deep learning, we would like to build very complicated neural networks, but we don't have circuit rules to help us construct the network. And this makes constructing complicated neural networks challenging. So the question is, what are the circuit rules for building neural networks? Can we figure those things out? So to think about this problem, we want to actually break it up into two pieces. So we want to ask, what are the good properties for an individual layer? And then we want to ask how to keep those under composition and concatenation. So in other words, we want to think about building a neural network by first taking individual layers and understanding individual layers really well, and then put individual layers together and try to understand how that thing behaves once we combine these things. And we have two rules for we call them composition and concatenation. But first, let's just look at the first question. And I have an example of a simple neural network layer, which is just a linear layer, which basically does a matrix multiplication. And I'm going to change the weights of this layer by a delta W matrix. And okay, and what I'm going to claim is that if you want your linear layer to have really good properties and very easy to train, what you should do is you should impose these spectral conditions on how big the weights are and how big the change in the weights are. And these are conditions on the spectral norm of the weight matrices. And in particular, we have like a particular. Are people familiar with fan out and fan in of a matrix? It's just the engineering terminology to say the fan out is the output dimension and the fan in is the input dimension. And the claim is that if you scale the spectral norm of the weight matrix and the weight update according to these rules, then what happens is if you scale the dimensions of the layer, like you make the layer wider by scaling, the optimal learning rate, this learning rate will stay the same even as you scale the model. So like intuitively, it's like you've got your neural network and you make one of the layers wider and then you try to train it again. And because you did these conditions, because you did these spectral scaling conditions, you can use the same learning rate on the small model as the big model. So that's my claim. I've not really like said why that's the case. But we have some like prior work which really looks into this. And I'm just claiming that it is the case. And like I could talk more about it, and maybe if someone has a question about it, like I'm looking at the chat, but otherwise I'm just going to keep going. I'm just for now just say kind of claiming that we sort of know how to think about a linear layer, and it involves scaling the spectral norm of the initialization and the spectral norm of the weight updates. Okay, I shall keep going. So this was implemented in a Hugging Face repository called Nanotron. So people are interested in it. So Pablo asked, essentially you were defining the distance in the weight space as being this ratio, right? So what we're saying is that if you have a linear layer, what I'm claiming is that the right way to measure distance is by using the spectral norm, and not quite just saying like you typically want to take steps of spectral norm 1. What I'm saying is you want to take steps of spectral norm, this ratio in the green box. And first, if the matrix is square, fan out over fan in is 1. And so this is just saying that you want to take steps of spectral norm 1, essentially. But there's a slight difference if you have a rectangular matrix. But yeah, thank you for the question. But that's hopefully that's not a too surprising condition that if you have a square matrix, you should initialize it to have spectral norm 1, and your steps should have spectral norm proportional to how big the initialization is, using the learning rate to make them a bit smaller. But that's roughly the argument. So the next question is, like what I claim is that we sort of know how to deal with individual layers, and it's roughly like assigning operator norms or assigning them the spectral norm and using the spectral norm to. Sorry, I'm reading what Andre says. I'm not sure exactly what you mean by the similar to the receptive field, but I'll just keep going. So in this talk, I mainly want to discuss this paper, which I worked on with some really amazing co-authors. And it's addressing this second question of let's suppose that we sort of know how to deal with individual layers in a neural network. How do we deal with composing and concatenating them to build bigger neural networks and to understand how to measure distance in the weight space of general neural networks? And I'm just going to start by telling you about a software package that we wrote. And this is kind of like the end result of us thinking about this a lot. And it's built on top of PyTorch. And basically we import, we call the package modular. And to use it, you start by importing your basic layers. And then you build, a neural network, here a multi-layer perceptron or an MLP, by composing layers. So we use the at operator to do composition. And then simply by composing layers, we automatically build an initialize function. We get data, and for each step, we get the output of our neural network. We compute the loss. We do the backward pass, and then this is what's new is we get the gradient. This is very similar to just standard PyTorch program, but now we get this normalized function, which is automatically constructed during construction of the MLP. So this is the general spirit of this package, is that as you build your neural network, you automatically build a normalized function, and it's constructed recursively from the submodules that are used to build the network. And then once we've normalized the gradient, which happens in place, we subtract it from the weights, and then we zero out the gradient, and we go to the next step. So the idea here is that we're going to build a very clever normalized function. And by doing this, it's going to make our training much more stable and much more scalable. So in particular, you can use the same learning rate as you scale the width or the depth of your model. And it's compatible with any array programming package. So we build it on top of PyTorch. Someone called Jack Gallagher ported it to JAX, and I also wrote a NumPy port. So it sort of can be, but this idea can be put on top of existing numerical software packages. And the main claim here, I'm just going to show you the main claim of the main empirical claim that we have at the moment. Although there's a lot of work happening at the moment, which I haven't had time to put into the talk, but essentially what we did is we took a nano GPT from Andrei Karpathy's package, and we trained it for 10,000 steps on a data set called Open Web Text, and we used Adam as the base optimizer, and then we tried switching on and off normalization. So by normalization, I mean the special normalize function that our package gives us. And this first column is showing the performance without any of our stuff. This is just a re-implementation of NanoGPT. And what you see is that as you scale of your neural network, what you see is that the learning rate is drifting. Like if I'm at width 32, I need to use this learning rate. But if I'm at width 1024, I need to use this learning rate way over here. So the optimal learning rate is changing as I scale the width. So that's bad. This is our special GPT architecture, which we think in certain senses improves the standard one, but still just training with regular Adam. And as you can see, the drift got a little less severe, but it's still kind of bad. And then this is after we switch on our form of normalization, and you can see that now the drift is corrected. So yeah, that's basically current package. Is basically you build your neural network in this package. You can scale the width, and like the sort of the training dynamics are invariant. Although the loss is improving, but the optimal learning rate is not drifting. And we can do the same. This is just doing the same thing for depth. By coincidence, Adam sort of gets the depth scaling right without the normalization, but the normalization doesn't hurt. And in the paper, we show some other things like you can train if you do normalization on top of SGD instead of Adam, you can still train the transformer. And the learning rate transfers across other dimensions like context length. But this is the main empirical claim of the talk. There's actually some really exciting things happening at the moment where if you take these ideas a little bit further, you can actually make the training much faster than with Adam. So I'll talk a bit about that at the end, but most of the talk is now going to be quite theoretical. So I just want to stop and I'll drink some water. And if anyone has questions at this point, feel free to ask. Because after this point, I'm just going to start talking about theoretical stuff. Okay. So, yeah, the part two is called the theory of modules. So this is basically our attempt to build the best possible theoretical understanding of deep learning that we possibly can. We want to understand everything that's going on inside the neural network as well as we can. And we've developed this theory to try to help us do that we call the theory of modules. And our idea can be framed in terms of something called the combinator pattern, which is this is the combinator pattern. Complex structures are built by defining a small set of very simple primitives and a set of combinators for combining them into more complicated structures. So for us, we have this abstract type that we call a module, and a module is just something with inputs, weights, and an output. And given two modules, we have combinators for producing new modules. The first combinator is composition, and we think of this as modules in series. And the second combinator is concatenation, and we think of this as modules in parallel. And we think about taking our input. For concatenation, you get the input and you get two copies of it, and you pass one copy to the first module and one copy to the second module. Whereas for composition, you take the input and you pass it through the first module, you get the output, you pass it through the second module. And the claim is that using these, basically a library of simple modules and these combinators, you can build really, it seems like any neural network that you want. So I want to demonstrate that a little bit. And we want to show you how to build these what we call circuits. So addition, adding two modules, we concatenate the modules, and then we pass to a special add module, which just adds the forward functions essentially. Scalar multiplication, you can compose with a scalar multiplier module, which just takes its input and multiplies it by scalar. And using these, we can build a residual block with block multipliers A and B by concatenating, composing with scalar multipliers, and then adding. So this is a sort of circuit perspective on basic neural network building blocks. Again, if anyone has questions, just just shout out, because it may be honestly it may be more interesting to discuss a little bit, but if not, I'll just keep going. So we kind of categorize modules into 3 different types. We call them atoms, bonds, and compounds. So atoms are like hand-declared modules, like linear convolution embedding. Bonds are like atoms, but they don't have weights. So things like nonlinearities and things like functional attention, which is the part of the attention module that doesn't have weights. And then compound modules are combinations of atoms and bonds. Like for instance, a multi-layer perceptron. So this is just composing here to build a compound, but we could also have concatenation. So okay, module sensitivity. So the big thing that we want to understand is if we change the what is the sensitivity of a module to changing its inputs and weights. So if we change the inputs, how much do the outputs change? If we change the weights, how much do the outputs change? And the major goal of our package is to be able to predict these things, like how much the outputs change based on how much the inputs and how much the weights change, and to be able to do this really for any module. And we break this up into a kind of recursive style question where we say, if we can predict the sensitivity information for atoms and bonds, then how do we predict it for compound modules? I'm about to just kind of hit you with a lot of math and a lot of definitions, and I don't know if people are following or not. But does anybody have questions about what I'm about to do? Let me just try to sketch out at a really high level what's going on. So we're going to define something called a module. We're going to define something called a well-normed module. I'm going to define something called module composition, and I'm going to define something called module concatenation. And the idea is that through the way that we define these things, we're going to kind of give ourselves a way of automatically estimating sensitivity information for any module. And that's what we want. And once we know how sensitive modules are, life's going to get a lot easier, because setting the learning rate is going to be much easier, because we're going to now know what the learning rate actually means, because we're going to know how to interpret it in terms of how sensitive the modules are. So that's what we're about to do. Okay. I guess it would be helpful to know, is anyone following? Because if nobody's following, we can just chat and try to figure out what's going on. Because honestly, there's already a recording of this talk on YouTube, so it's more valuable just to discuss. But I don't know. If anyone can tell me that they're following, I'll keep going. But otherwise, I'm just gonna wait. Okay, thanks, Samuel. Okay, thanks, Pablo. I'll keep going. So we define a module. Remember that a module is something with. Hi, Andre. A module is something with inputs, weights, and an output, and then it has. Yes, exactly. Yeah, Thank you, Matteo. That's exactly what it's supposed to be, like automatic differentiation, but for sensitivity information. Which is, I claim, is the missing piece of it's what we don't have in deep learning, and it's why the training algorithms are kind of annoying, because we don't know what the sensitivity of our network is. But if we did, then life would be easier. So we define a module as something with inputs, weights, and an output, and 4 attributes. So forward function, a number, which is the sensitivity, and currently this is an abstract definition, but the sensitivity is supposed to be a number which tells us how sensitive the module is to changing its inputs. And a mass, which I'm going to defer talking about for now, but the mass is also a number. And actually, roughly speaking, the mass is something like a layer-wise learning rate, or a way to tune how important different modules are towards the learning. But let's not focus too much on that now, and we can come back to it. And then the really important thing is we give each module a norm on its weight space. So the norm is a function which takes in a weight, the set of weights for this module, and returns a number. But this is an abstract definition, and a lot of things satisfy this definition, but we don't care about those things. Like in practice, we care about quite a limited set of modules. So we need some guidance on how to how to choose the properties of a module. If we're going to be module designers, like we're going to design a linear layer, we need some guidance on how to do that. And we come up with this second definition of a well-normed module. So for a module to be what we say well-normed, it has to have a norm on its input space and a norm on its output space. And this is where we claim that we sort of know how to pick those input norms and output norms already. And it's related to the fact that we know how to do layer norm, or we know how to do RMS norm. We sort of know how big we want the inputs and outputs to be. So we kind of have that information usually. So the real content of the definition is these 2 properties, which are bounds on the derivative of the module contracted with a change in weights, or contracted with a change in input. So the first statement says that the module, if we change the weights to the module, then the size of the first order change in the module output is bounded by the module's norm, the size of the change in weights in the module's norm. So this is the statement that the module's norm, like the size of a weight change in the module's norm, bounds the first order change in the module output that is induced by that weight change. So this is just a formalization of the statement that we know how to predict how much the module changes in response to changing its weights. And the second statement is the same thing, but it says that the amount that the module output changes up to first order in response to a change in input is bounded by the size of the change in input multiplied by the sensitivity parameter of the module. So these are 2 sensitivity statements, and if the module satisfies these statements, in other words, if you pick the module norm and the module sensitivity such that these statements are true, then we say that the module is well normed. So this is the guide of how to pick. If you're trying to design a module like a linear module, this is the guide about how to pick the sensitivity number and the norm. You should pick them to so that these inequalities hold. So I want to take a little break and just give you an example. So let's think about a linear module. And we write its forward function as a matrix multiplication of a vector. this is a definition, so we can just define its sensitivity to be 1. I haven't told you about mass yet too much, but let's just set that to 1. And let's set the norm to be the spectral norm with this dimensional factor. And then my claim is that you can check that if we set the input and output norm to be the RMS norm, or the root mean square norm, and then so long as the inputs are less than 1 and the weights are less than 1 in their respective norms, then the module is well normed. So like, there's an exercise to prove this, but that's the claim. And now how do things differ to an embedding module? Because on the surface, an embedding layer in a neural network is kind of like a linear layer. They're both, the weights are both matrices. I can, sorry, I can't understand that. Okay, I am looking at the chat, but
it's related to the registration in the event, so don't worry.
I understand, but tarde.
Okay.
So embedding module is basically very similar to a linear module in the sense that the forward function of both modules is a matrix vector multiplication. And we can give it sensitivity 1 and mass 1, but we give the embedding module a different norm. We say that its norm is the maximum RMS norm of the columns of its weight matrix. And the reason that we do that is because we also want to give a different norm on the input space of an embedding module, and although the same norm on the output space. And the reason we do this is we think of an embedding layer in a neural network as passing in a one-hot vector, which sort of picks out one of the columns. And then you think about the column as being fed to the next layer in the neural network. So it's kind of, there's a different semantic, so there's a different meaning behind an embedding module compared to a linear module. And for that reason, we sort of equip it with different norms on its input and output space, and a different norm on its weight space. But once we do that, the embedding module is well normed under the same conditions as the linear module. Okay. Anyway, this is like, even just this slide alone is like something that people in the community do not understand well. But something I want to emphasize is that because linear and embedding modules have different semantics, they're used in different ways, we should give them different norms. And that's going to, later on, that's going to imply that when we train the network, we should actually sort of use different optimization algorithms for the different layers. And this is something that is not, even people like the biggest, fancy tech companies do not understand this point, or many of them do not understand this point. But I think it's an important point about deep learning. So anyway, those were supposed to be some examples about how to design individual, what we call atomic modules, or the basic building blocks of the neural network. And then what we did is we then wrote down these rules for how to compose modules, and how to concatenate modules. And what you notice is that if we compose modules, we give rules for composing all the attributes. So we compose the forward functions, we multiply the sensitivities, we add the masses, and for the norm on the weight space of the module, we take the max weighted by coefficients, so the max norm of the two subnorms. And I just want to give you a little bit of intuition for why we pick these coefficients P and Q. So first of all, the input sensitivity of the second module couples to the norm on the weight space of the first module. That's the idea that if you compose two things and the second one is very sensitive to its inputs, then when you change the inputs of when you change the weights of the first module, you need to be very careful because the second one is sensitive. So the first module needs to be careful because of the fact that the second one is sensitive. So that's why the norm of the first module should couple to the sensitivity of the second module. And hopefully that's an fairly intuitive idea that if you compose two things, so Eduardo is asking a question, which is, if I define a well-normed module, can I use any value for mass? And Eduardo is noticing that the mass does not appear in the definition of well-normed, and that is true. Yes, that you can pick any value for the mass, but the claim is that there's a kind of good way to set the mass that's separate to the definition of well-normed module. But I haven't discussed that yet. But hopefully, I think on the next slide, I'll try to discuss it a little bit. But yeah, that's a great observation, that well-normed definition does not involve the mass. Okay, and then the definition of module concatenation is similar to module composition, but they're different in the sense that the sensitivity of the second module, because there's less coupling in a concatenation than in a composition, so the sensitivity does not appear. And similarly here, to get the combined sensitivity, we just add the sensitivities instead of multiplying them. Okay, but at this point, the thing to emphasize is these are all just definitions. So anyone is allowed to define anything the way they want, and everyone should have that freedom. But the question is always, are these good definitions? Are these helpful definitions? What do they allow us to do? So the reason that we like these definitions is that they have some nice properties. So the first one is that the combination rules that we gave are associative. So if let's say you compose 10 different things, it doesn't matter. And so you've got a chain of 10 modules. It doesn't matter if you first compose these two and then compose them with the next one, then compose them with the next one, or you start at the other end of the chain and you kind of work this way, you get the same thing. So it's a good to have associativity. The second property is that well-normedness, that definition of being a well-normed module, is preserved under composition and concatenation. So this is a really powerful property, and it says that as long as you have a library, you build your library of atomic modules, things like linear, convolution, ReLU. You build your library of atomic modules. Then anything that you can, and you make sure that all the atomic modules are well normed, then anything that you can build in your library is automatically well normed. So in other words, this is the statement that if you can characterize the sensitivity properties of your atomic functions or your atomic modules, then you can automatically infer the sensitivity properties of anything that you can build out of them, any neural network that you can build in your library. So this is sort of what everything was set up to do. I'm not going to tell you how to prove. You have to prove this. The proof is not actually it's not a crazy proof. It's more or less just applying the definitions and then using things like the chain rule. But it's worth trying to think through exactly why this is the case. And then, okay, the final thing is the mass. And this is where the mass comes into things. And it's the idea that the mass gives you the freedom to sort of tune where the feature learning happens in your neural network. And the motivating example for this is you think about training a transformer, and it's got an embedding layer, it's got a bunch of blocks, and then an output layer. and it's sort of unclear how much you want to train the embedding and output layer relative to the blocks. And it's very difficult to answer that question a priori. So we have a hyperparameter called the mass. And in practice, when we tune this, we're only tuning one mass hyperparameter, which is the mass of all the blocks relative to the input and output layer. But so another way to say this is that there's still freedom. We've not nailed down all the degrees of freedom in the neural network. There are still some degrees of freedom that we don't know how to set, and that includes the mass. But we can prove what we are able to say something useful, which is if you give like this module mass 1 and this other module mass 5, then up to 5 times more learning can happen in the mass 5 module than the mass 1 module. So the mass gives you the ability to choose where the learning happens in the neural network. So it's analogous to the idea of layer-wise learning rates or tuning different learning rates in different parts of the network, except it gives you much more precise understanding of how much learning is happening in different parts of the network. If you just have layer-wise learning rates, you don't really know actually how to translate that into how much learning is happening, whereas mass makes that easier. Okay, so I keep going. And I'm noticing that the time, it's like nearly been an hour, and I think the slot is like an hour and a half. I think there's probably 10 minutes left of the talk, and then like I guess we can just do questions. But yeah, I'll try to wrap up quickly because I think it would be fun just to see if people have questions. But a big part of the work is the fact that actually you can take this theory that we built and you can get it working up to second order. What does that mean? Well, we define something called the sharpness of a module. And a sharpness is defined by 3 coefficients, alpha, beta, gamma. And it's similar to the definition of well norms, but it's about second derivatives this time. And we've got 3 statements. The first is about second derivatives with just respect to weights. The second statement is about the kind of mixed second derivative, where one derivative is with respect to weights and one is with respect to inputs. And the third one is with respect to inputs. Okay, and the way to think of these is they're kind of like generalized eigenvalue statements. So you should think about like alpha, beta, gamma roughly as being like the top eigenvalues of the Hessian of the module, except they're not really eigenvalue statements because of the fact that we've got general norms appearing. If everything was like a Euclidean norm, then these would basically just be eigenvalue bounds or spectral norm bounds on the Hessian. But because we have general norms here, these are more general statements than that. But anyway, the point is that we can write down kind of composition and concatenation rules for these sharpness coefficients. And then we can prove that the neural network loss functions are smooth in the norm of the top level module. And we can also show really interesting things like the smoothness constants or the bounds are actually can be non-dimensional in like the size of the network. Like you make your residual network deeper or wider, and the smoothness bound is actually invariant to the width or the depth. So that's the big idea. And the caveat is you need to have a smooth error measure. Like square loss is smooth for this purpose. So if the error measure that you like use to measure error on the ultimate outputs of the neural network is not smooth, then you're kind of out of luck. And similarly, the components need to be smooth. Like this would not work for ReLU because ReLU is not a smooth nonlinearity. But if you use GLU or ReLU squared, I think. I need to double check, but yeah, like as long as you have a smooth nonlinearity, then you're in business with this slide and a smooth error measure. Anyway, this is like this is like extending that idea of the talk is about kind of automatic differentiation for sensitivity information. Well, this is about kind of automatic differentiation for second order sensitivity information. So it works for both first order and second order, which is something nice. Okay, and I think this is the final slide of the technical part, and then I just zoom out a little bit. But why do we normalize? So roughly what we've been trying to do in this whole project is to build non-dimensional and tight Lipschitzness statements about our neural network, get the norm that those statements hold in, use that norm to normalize the weight updates, and then our learning rate will transfer. So this is the thesis of the project. So if we can get Lipschitz constants, which are independent of the width and the depth of the network, and these Lipschitz bounds kind of hold quite tightly across scale, then controlling the norm of the weight update will give us control over how much the network output changes. So this is what we were talking about right at the beginning. And so formally, we want this kind of statement to hold quite tightly, which says that the norm of the weight update in the module's weight norm bounds how much the outputs can change in the output norm. And the tightness of an inequality of this form somehow depends on some notion of alignment between the weight updates and the input to the module. And this is something, there's another series of works called Tensor Programs looks at this, but in order to prove such alignment statements, they rely on things like assuming that the batch size is small relative to the width. But this is maybe outside the regime of modern training, where we may in fact actually have batch size much larger than width. So it's unclear whether this tensor programs approach can be applied, but basically the approach that we're advocating for does still apply. So I just want to wrap up by giving you a sense of what I think are the exciting directions for this, for these ideas. And so something I've been really excited by at the moment is the shampoo optimizer, which there's a paper on it, and it can be a little difficult to understand precisely what it's doing. But I came up with what I believe is a kind of simplifying perspective, which is that if you take this shampoo optimizer and sort of disable the accumulation, then what you realize is that the weight update that shampoo uses is equivalent in direction to solving something called a steepest descent problem under a particular norm called the spectral norm. Steepest descent under the spectral norm. And I wrote this up in a Twitter thread, and then I gave a demonstration of how to implement this idea in the Colab notebook, and I can share my slides, or I'll post them on my website. And there's a Colab for implementing this, and I showed that just this very simple idea can actually give a big speed up in training. And since actually, like in the last couple of weeks, someone called Keller Jordan, who's an independent researcher who lives in San Francisco, has sort of taken this idea and innovated on it a lot, and is getting he calls it like speed running, nano GPT speed running. And the idea is to train a transformer as fast as he possibly can. And he's getting like actually quite a significant speed up by using this technique over just using add-in. And it's something like, oh, thanks for sharing my website. I don't think I've shared these slides there yet, but I will do that. I think if you go to my Twitter, then like you can somehow find them, but I will post the slides on my website. But okay, this Keller Jordan, who is a speedrunner in deep learning, is like using his improved version of this technique to like get speed records for training nano GPT. So it's like really exciting. and it's going to be interesting to see how things develop. I think that beyond speed, I think that we can also use these ideas to make more robust deep learning models by having understanding of the sensitivity information. Maybe they can help with adversarial robustness. Yeah, better than going to my website. I'm just looking at the chat. Like, don't go to my website. Go to Keller Jordan's Twitter. It's where everything is happening. That's what I recommend. But anyway, I think it could potentially be used to understand uncertainty information in deep learning through something called normalized margin. Here is sorry, I just saw Samuel's message. There's some, we built on past work. I highly recommend this paper called Autobound by some researchers at Google, which is related to this idea of automatic differentiation for sensitivity information. They inspired us a lot. And then here's this package. Yeah, there's a link on this slide which takes you to some docs where I tried to present like a more. There's also the paper, but the docs are a bit more accessible, if on the other hand not as detailed. But yeah, I'm really honestly I'm really grateful for the chance to to speak here, and I'm grateful for Teo for the invitation, and I'll just stick around and would love if people have questions I can try to answer them. But yeah, thank you again for having me.
Thank you for accepting our invitation. Thanks for the talk. Oh, we have a question from Andre.
Andre, what do I think about using lasso as a loss function? So by lasso do you mean L1 penalty, or could you say? Thank you, Kelsey. What do you mean by lasso, Andre? And what do you mean by, if it is L1 penalty, what do you mean by using it as a loss function? Or do you mean? Yeah, I'll give you a chance to.
Meanwhile, I want to point out, like, I love your analogies, and like loved your analogy with the circuit about the parallel and the sequential. Amazing presentation.
Thank you too. I appreciate that a lot. So Joel De Silva has asked, how can I learn more about Metrized deep learning? So I would go to these docs. I hope I collected some links there. I'm not sure. My Twitter at the moment, I've just started tweeting like anything. I don't know. That's maybe a good place. But I gave, honestly, today I'm a bit ill, and I gave a presentation to Cohere, which is another organization, and that's posted on YouTube. It's the same presentation, but I have a feeling I just gave a better delivery then, but I'm not sure. There's this paper called the modular norm paper, and we also just wrote a new paper that we call an anthology, which goes through past optimization algorithms and tries to cast them within this framework of metrized deep learning. So that's something else. But yes, I don't know what the best way to learn this stuff is. Honestly, this paper that we call the anthology, it's called All Optimize the New Norm and Anthology. We wrote it to be as accessible as possible and to try to motivate the reasoning, instead of trying to present like the most advanced version or something like that. So that is probably a good starting point, and I would recommend reading that paper and then just reading the modular norm paper.
Do we have more questions? Feel free to ask.
Yeah, I can see if I can join the chat. I just think it may ask me to log in. And I'm not sure if I'm logged in. Okay.
We just had a question from Juliana in the chat.
Let's see. Hi, Jeremy. I have a question about your studies. Do you have a background in computational theory before going into this topic? Yeah, so my background, well, I did undergrad in physics, with some experimental physics and some theoretical physics. For grad school, I did a PhD program called Computational Neural Systems at Caltech, but I sort of was mainly in the CS department. So I had interactions with computer scientists. And then for this particular project, I worked a lot with like a very talented pure mathematician who happens to be my friend from undergrad. And he was a pure math, very good at pure math, but like was looking to transition into AI. Um, and that he honestly he to a large degree is there's a much more mathematical, like my work in the past has been like trying to do math, but this has, I would describe it more a kind of pure math flavor of like, let's just define stuff and almost like kind of from my perspective kind of solve the problem by just coming up with really good definitions. um and I'm honestly not responsible for that. That's my collaborator Tim Large. But so he had a pure math background. Yeah, that's something that I'm really liking about deep learning is that it's the, you know, there's that inspiration of like kind of neuroscience. There's like the computer science aspect, and then there are like interesting mathematical problems. And there's of course also like a big physics influence in the field, a big psychology influence. I think it's a really exciting area to work in because it feels like we're bringing all these different ideas together. Yeah, that definitely inspired me towards going into this field. Right. Yeah. Yeah. Linguistics is a very beautiful area. I'm gonna try to see if I can send this. I really want to send this. I think I can send it to Teo in the private chat, and then maybe he could.
Yes, I can do that.
Okay, I just because I can comment in the private chat, so I just sent Teo a paper. This is like a very just intended to be a very accessible introduction.
Let's see. I think yeah, it's in the chat now.
Okay, does anyone have any more questions? I'm really happy to answer. Uh, there are rules for calculating the module sharpness. So like you get alpha, beta, gamma of the two submodules, and then there's a formula. It's written down in the paper, but I didn't write it down in the slides. But there's just a formula. Like if you have two submodules and they each have an alpha, beta, gamma, there's a rule for combining them to get the alpha, beta, gamma of the composition or the concatenation. But we've not actually yet used that information in practice. At the moment, that's more a theoretical thing. But it would be really cool if that information is useful. But we're kind of not there yet. It feels like we need to solve a couple of other problems first. But okay, let me know if there's anyone has more questions. Thanks, Joel.
Last chance for the questions. Okay, Jeremy, thank you so much for your presence here. It's been amazing presentation. Thank you for that. Truly inspiring. I would like to see more about this topic, and I'll for sure read the article that you sent. Thank you for that.
No, yeah, thank you, Teo. This was a really nice opportunity, and great to chat with you a little bit, and really appreciated all the questions.
Very good. Hope you get better in your health
Yeah,
situation. Um, well, nevertheless, you did great.
okay.
Very good. We end here. Tomorrow we have more 3 presentations, so stay tuned. Um, um, Follow us in the social media, and yeah, see you soon. See you tomorrow. Thank you, Jeremy. Again, see you.
Bye.
Bye bye.